Hello, dear, and welcome back. So, we are discussing mass spring damper second order system with damping with an example of mass spring damper model. Okay, and we are considering free oscillation. That means only perturbation is there. And what we have observed that the general solution um, is a little bit is a little bit um, special. It will have three cases we are discussing, right? Let us just try to understand that this is my general solution. Two constants A1, A2, this plus because system is linear and principle of superposition holds. Again and again I am telling. Otherwise you cannot figure out general solution. The system is linear in nature, okay? Some of my students ask, sir, characteristic equation is quadratic, then how can it be linear? No, that has nothing to do with system's linearity. And characteristic equation is actually describing the order of the system, and depending on whether it is quadratic, whether it is cubic, you will get the number of roots, that is the number of solutions. And if system is linear, the solutions can be added. If not, then you cannot figure out the general solution. So since your solution is linear, then we can add them together. And you see, we are considering the underdamped situation. Underdamped situation has, you see, the imaginary part, right, I, which is root over of -1, and uh, wherever the root has some imaginary part, Euler equation is telling you that there will be some oscillation. Okay, e to the power I theta equal to cos theta plus I sin theta, Euler equation. So using that, just theta here is root over of 1 minus zeta square times omega t. So this is theta. If you put it here, do some exercise, and then you will, after simplification, you will get the general solution. Okay. This is called damped circular frequency, root over of 1 minus zeta square times omega, because you see omega is the natural frequency of the system when there is no damper. Okay, so root over of k by m, but when there is damper, so that oscillations, the natural frequency will be damped. Okay, and you have seen that for damped system there will be no oscillation at all, it will be so damped. Okay, and here of course there will be some oscillation. We are trying to consider what will be that oscillation, and we have a general solution like x, small x equals to capital X. This is the amplitude of oscillation, e to the power minus zeta omega t sine of omega dt plus phi for zeta less than 1. Everybody is with me? So now characteristic solution, right? Now we can put phi equal to 0 without loss of generality, because we are interested to actually simplify it. Okay, and how the oscillation will be there. So it will start from 0. Okay, but if it is not, then of course phi will be having some value. But for simplicity, we are assuming this is 0. So my solution is this. So I can now look here. I can, for maximization and minimization, I can just I'll have to differentiate this. Okay, so for maximum minimum points of the curve is set to 0. I differentiate and it's set to 0. So x dot, I am differentiating, right? So this is x dot, right? So you see it is a minus zeta sine, so all kind of, right? So this is the differentiation with respect to time is giving you, and that we are putting to 0. Now look here, case 1, e to the power minus zeta omega t. If this is a product of two quantities, 0, the omega is not 0 because it is circular natural frequency of a system. Amplitude of oscillation cannot be 0. There will be, if oscillation is there, there will be amplitude of oscillation. So these two things will be 0, either of these two things. Now, if e to the power minus zeta omega t equal to 0, so exponential something will be 0. When it can happen? When actually t is infinitely large. It can happen so. And that means that this condition means, okay, the amplitude of oscillation, this intra term, right, will be 0. Okay, whatever you start from here, amplitude of oscillation will be 0. If here it is infinity, I am not saying you, it is infinity means very large. If it is very large, then this damping will be considerable amount, and then the amplitude of oscillation will die down, will be 0. So this signifies that when this will be 0, then amplitude of oscillation, that is x, will be 0. And then when this will be 0, this is going to give me a very interesting thing. This is actually, you see, minus zeta sine omega dt plus root over of 1 minus zeta square cosine omega dt equal to 0. And from here you can calculate tan omega dt, which is equals to root over of 1 minus zeta square by zeta. Just take a notebook. How I am getting this, you see, I know sine theta equal to plus minus tan theta divided by 1 root over of 1 minus tan square theta. Just check. This is identity. So sine omega dt is equals to, from here, you see, from here, sine omega dt equals to root over of 1 minus zeta square, and sine omega dt equal to plus and minus, plus and minus. So from here you calculate. Okay, getting my point, huh? So from here you can calculate this is equal to 0, means sine divided by cos. This will be going there. Simple. Just take a notebook and do it, please. So tan omega dt will be equals to root over of 1 minus zeta square by zeta. Okay, and sine theta is plus minus this because we are trying to figure out the envelope. That's why plus minus, and we are using this identity. And sine omega dt will be equals to root over of 1 minus zeta square and minus root over of 1 minus zeta square because of this plus minus sign, right? Just simplify this quantity, you put it here, here, simplify, you will get this. Okay, this is an exercise. Take a notebook. So that's great. So we have got, now we are able to plot the result, the solution, x versus omega dt. Omega dt is actually, we have taken to simplify the graph, otherwise x versus t also you can do. It's a constant. Now, you see, the solution is telling you, look here, the amplitude of oscillation will die down slowly because of this quantity. Okay, and the oscillation will be within the envelope which you have got, plus root over 1 minus zeta square minus root over 1 minus zeta square. You see, this is the exponent. This times, this is times x e to the power minus this. Okay, so this actually is, you are getting my point, right? So putting here and here, you will get that exponent curve as if this is my envelope, and within that the oscillation will take place. And since this is asymptotic in nature, it will die down. X will die down, and this is ensuring that when it will happen, it will depend on the value of zeta and omega, natural frequency. Depending on that, t will vary, right? So if the zeta is very less, that is too much underdamped is there, so there will be many oscillations before it die down. And if zeta damping factor is actually high, okay, 0.9 or something like that, 0.8, 0.9, it varies from 0 to 1, right? So 0.1, 0.2, like that, 0.9. So these are high damping, low damping. So if these are the values of zeta for the same natural frequency of a system, t will be large. So this is a meaning of asymptotic curve, right? So asymptotically x will be 0. You understand that? Now come back. So this is underdamped situation. So there will be oscillation. Now Let us come back to case 3 when zeta equals to 1. We call it critically damped situation, and we will just exploit um, this and this solution for underdamped, and we will exploit that to get a fairly clean solution for critically damped system. Okay, so here it is. I am rewriting this. Okay, so this is our solution, right? So omega d equals to this omega dt. So this is equals to omega d. So omega dt plus. You understand, right? So here it is. From 13 we are getting this. So when zeta equals to 1, then what will happen? You see, zeta equals to 1, then zeta equals to 1 means omega d is tending towards 0. Okay. So for finite time, sine of small quantity which is tending towards 0, sine theta will be theta, that is omega dt, and cos omega dt will tend towards 1. That's, again, class 12 trigonometry. If the angle of oscillation is too small, sine theta will be theta, cos theta will be 1. So now from here, what we are getting is the following. X is e to the power minus omega t, because zeta equals to 1, times a dashed omega dt, you see, omega dt, because instead of this we are writing this omega dt, plus this is becoming 1, so this is the case. Now here you see, I can write this as a constant a, this constant b, and this as constant a. They are two distinctly different constant now. So x equals to a plus bt e to the power omega t. This is the more logical and correct solution for critically damped situation. Two constant, different, arbitrary different constants are there. So for studying zeta equals to 1, I had to study first underdamped situation, and from there I took the solution, and from there I deduced the solution for critically damped situation. So critically damped situation, if I plot, again you see there is no sinusoidal term. So there will be no oscillation at all. So wherever you start, you see, with time, the amplitude of oscillation, x, the amplitude of oscillation with time, okay, depending on a and b value, of course, it will be asymptotic. Because of this exponential term, the decay will be there. This is called critically damped situation. Critically damped situation in control, when we'll study control, we want controller should behave in dampening error. It should behave like a critically damped system, okay? Because it will ensure that error, we'll talk about those things in control. The errors will be very fast, will die down. If x equals to error, system error will die down very fast. Now you see these three comparative curve now I am drawing. So this is overdamped system. When zeta greater than 1, this is underdamped. When zeta less than 1, so there will be oscillation. It will depend that value of zeta, how many oscillations will be there, but there will be oscillation, okay, because of this e to the power I term, minus I term, right? And this is what you have got now, critically damped. So critically damped system is desirable in case of control. You know, control is all about controlling somebody, right? So I am giving an example. Say parents want to control his child, right? And they want even they want a critically damped child's response should be critically damped. Meaning what? Suppose the parents are telling child, don't do that, and if the child is behaving like overdamped, well, parents has told me not to do it. It will take long time to obey. So it will try to go here, and it will take long time. So this is spoiled child, right? It will try to not to listen what parents are telling. Underdamped, on the other hand, well, child is not so spoiled. So whatever instruction has been given, with some hesitation, no, 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 I will not do. Okay, I will do it tomorrow. But eventually it will obey. That is the meaning. Just I'm giving analogy that if x is error and parents wants that error to zero, that means do this thing and do not do that thing in that command. Okay, undamped system means actually with some hesitation, ultimately child will obey. But critically damped system, child is too good. So whatever parents are telling, child is doing that. Okay. In control perspective, also critically damped system is very much desirable. Okay. We'll discuss. Okay. So mostly the background as far as control is concerned, we have created. Okay. Maybe next lecture we'll talk about a little bit about what will be the solution without going into detail, because this is good enough for our control, and we are not studying oscillation that is actually P, that is not equal to 0, is force oscillation. When this P is there, depending on the nature of the P, the system will behave. Okay, and we call steady state response, tension state response. Maybe we'll discuss a little bit about all this, because now so much background we have created in oscillation, and I think understanding control will be very much easier for all of you if you just um, listen these videos carefully, and we can solve many problems. We'll try to do that in the class. Many problems which will further help you to digest. But I think I was frank enough to explain the simple math content of second order system, and I hope that you have understood. If not, then come to the discussion forum. Till then, have a nice day, stay safe, and bye bye.